So question 6, you are given an array, in this case unsorted. Unsorted array B, and D in this specific case we have 2, 3, 5, 6, 1, 7. Now we are also informed that the content of B contains integers from 1 to n plus 1, where the n is the length of B. So since B here, the length is 6, so we know that the numbers inside is going to be somewhere between 1 to 7, but we don't know which one is missing, right? So we don't know which one is missing, and we want to find. Now, the missing one in this case is 4. Now, then we want to design algorithms to try to find this 4. So to find this 4, and we allow you to design different algorithms of different complexity. The lower the complexity, the higher the marks. Okay, so all right, so we're going to try from the simplest case, right? The simplest case is to do brute force, because you know that the numbers inside is somewhere between 1 to n plus 1. So then we just need to search one by one, and as long as we don't find it, then we just keep searching, and we're going to do that. So let's say alright, so we are going to go from I in range. So we know the number could be between 1 to n plus 1. So we're going to go from 1 to n plus 2, because we are excluding the last one. And each time, we will just do linear search. So we're going to be searching the array B for the value I, right? And if this happens to be less than 0, meaning that if we don't find the I when we do linear search on the B, it means that I is the missing one. So then we just need to return I. Yes.
This is a nested loop, right? The else search itself contains a loop also, right?
Inside the search, there is a loop, right?
So the complexity is n squared for this one.
In this case, the complexity is n squared, yes. Right. So I'm just reusing the linear search, but essentially it's the same concept.
Can I ask, if you use the function sorted, right? What's the
Sorted.
complexity? What's the complexity for that?
So what function again?
No, it's
Thinking
just
about the
sorted.
Python sorted.
Yeah.
Yeah.
Oh, I don't know what's the implementation there.
No, you just sorted then.
Yeah, then you need to tell me what is the complexity of the sort.
Yeah, I don't know actually. Sorry?
I think worst case is n squared. Not the algorithm is team sort, it's a mix of two.
So it depends on what is the
It can be
sorting
very
algorithm.
fast.
So one other way to do it is to sort it first, right? So let's say if we say we're gonna do insertion sort. So you're gonna sort B first. So once you sort B, then you're gonna get this, but in sorted order. Now the one that is missing is when you have a jump, right? So then you can do another for loop.
Let's go by that.
So from 0 to n. So because it's already sorted, you just need to see where there is a gap. So if AI is actually less than AI plus 1 plus 1, so that means that if the current number is less than sorry, minus 1, plus 1. I mean, at this point of time, it's already sorted, right? So what we're going to get is 1, 2, 3, 5, 6, 7. So we're going to go one by one, and we're going to expect that any number is the next number minus 1. So at any point of time when the next number, this number is less than the next number minus 1, and in this case it's going to happen here. So 3 is less than 5 minus 1, which is 4, means there is a gap. So the gap, where the gap is the missing one. So then in that case, we're going to return the value that we expect there, which is ai plus 1 minus 1. So that is the missing value that we are expecting that we don't find there. Now in this case, so the insurance sort, what is the complexity? So insurance sort is n squared. Then here you have another search, right? Which is O n. So n squared plus n. So then the overall is still O n squared. So then this is the second algorithm. So in this case, if you give the first one or the second one, it's still n squared. So then you can do better than this, right? Because we know that insurance sort is n squared, and it's the dominant one rather than the searching. So that means you can cut down the complexity if you use a simpler sorting. So the next one, you can also do merge sort, and then the rest is the same. So then the merge sort part is going to be O n log n. This one is going to be O n. So combined together is O n log n. Now this is n squared, this is O n log n. So if O n log n is lower complexity, so this will already get you a higher mark. And because the dominant one is the sorting, which is the n log n. So all this supposed to be B prime. Yeah. Alright, so by now we have done this in O n log n time. Now can we do better than that? What is better than n log n? N. Okay, how do we do it in n time? Yeah, describe it, yeah. How is it?
Like let's say you have 1, 2, 3, 5, right? So you know the missing number is 4.
Uh-huh.
So the supposed one we're supposed to have is 1, 2, 3, 4, 5.
Okay.
So you just sum the two and then you minus, then you get the missing number.
Okay, yep.
Yeah.
So we have 1. So we know that the number is going to be 1 to n plus 1, right? So 1 plus 1, 2, 3, 4, and so on. So if you were to sum them, we know what to expect. So let's call it the expected sum. So this is going to be summation from 1 to n plus 1, which is 1 plus 2 plus 3 plus 4, and so on, all the way to n plus 1. And this sum is going to be the same as n plus 2, n plus 1 divided by 2. So that's the total sum, right? And to compute this, you can do this in O1, right? It doesn't matter what the n is. You can always compute what is the expected sum. But then you need to know what is a missing number. So that means that then you then can count what is the actual sum. So then you can iterate in the B. So the actual sum, we're going to keep adding up all the elements in the B. So then you get the actual sum, you get the expected sum. So then in the end, to get the difference, you just return the expected sum minus the actual sum. So this one is ON, this one is O1. So O1, ON, O1. So then the overall complexity is going to be ON. Okay, you can do this because it so happens that the numbers that we are looking at is 1 plus 2 plus 3 all the way to n plus 1, and we know what to expect in terms of the total sum. So if something is missing, then whatever is not accounted for in that sum is the missing one. Right? Does anybody have another ON solution? Right, so there is another ON solution. So what we are going to do, so initially we know what the value of B is, which is 2, 3, 5, 6, 1, 7. So we know what to expect, right? Which is any number from 1 to 7. So we know something is missing as well. So what we're going to do is to create a flag array. And because we expect it's going to be 1 to n plus 1, so we're going to make this size of the flag to be a little bit longer than the B. And we're going to set them to zeros. So in this case, the index of this so this is to say that I have a flag that these are the numbers that I haven't found yet. So then I can go through the B, and if I find a number, I can then set the flag accordingly. So which means that for I in range 0 to n, so the BI, so the BI here is going to tell me what number I have found. So if I found 2, I can set the flag for number 2 here. So that means that the flag for this one minus 1 is equals to 1. Now, so what does it mean? It means that if I found 2, then I'm going to set this to 1. I found 3, I'm going to set this to 1. I found 5, so 5, I am expecting it in index 4, so this is 1. 6 is 1. 1 is 1. 7 is 1. So then there is only one number that is missing, which is a 0. So which means at the end of this thing, I expect exactly 1 0. Exactly 1 0 where the number actually didn't appear. So then I just need to do linear search for 0 inside the flag. And once I find that particular location, I just return that number plus 1. So then that is the missing number. So to form the flag is ON. To set the flag is ON. To search the flag is ON. So then in combination, they are still ON. So this is a little bit less efficient because you still have to do 3 times n, but overall the complexity is ON. So we can still give you the mark. for this one. Alright, so the thinking here is that for the same problem, often you can find different solutions. And if you can think of a solution that has lower complexity, generally we will reward you more. Then you keep asking yourself, can you come up with something even better than what you have thought of, right? So and that is going to get you to try to optimize your code even further. All right, any other clarification here?